Hi everyone, welcome back. So in today's video, we're going to be reviewing linear ordinary differential equations. All of the methods we're going to be covering in today's class were covered in B44, the prerequisite to this class, and so this will all be reviewed. So let's go ahead and get started with first order ODEs, linear ODEs, of the form dx dt plus a1 of t x is equal to g of t. With initial conditions x of t naught is equal to x naught. So recall one of the methods that we had for solving first order linear ODEs is using integrating factors. So integrating factors. And we actually happen to know what the integrating factor is for first order linear ODE, which is I of t is equal to the e to the integral from t naught to t of a1 of tau d tau. And note, of course, that we're using tau as the variable inside of the integration because it's also being used as one of the limits of integration. T is being used as one of the limits of integration. Now, occasionally you'll see me use the same variable as both a limit as well as the on the outside and on the inside. Hopefully that's not too confusing. It should be clear from context what is meant, though. I'll try to remember to use different variables. And anyway, so the whole point of integrating factors is if you multiply both sides, then one side becomes an exact derivative. So let's multiply this together. So we end up with I of t dx dt, and of course this is a function of t as well, plus a1 of t x of t. Actually, let me write this. I of t x of t is equal to I of t g of t. It turns out this is an exact derivative. By which I mean that the x of t I of t over dt is equal to I of t x dot of t by the product rule plus x of t I dot of t. Well, what is I dot of t? So actually, let me put this out over here. So we know that I dot of t is then going to be equal to, well, you take the derivative of an exponential, you're just going to get the exponential back again. So that's going to be equal to I of t times the derivative of the inside. But the inside is just an integral from t naught to t of a1 of tau, and so the derivative of the inside of derivative of an integral is just going to be a1 of t. And so this here is x of t times I dot of t, which is equal to I of t x dot of t plus x of t I of t a1 of t, which is precisely the left-hand side up there. So together, this implies that the x of t I of t over dt is equal to I of t g of t. We're going to use the standard abusive notation. And what we're going to do is we're going to take the integral of both sides with respect to dt. Now, of course, you can think of this as the integral dt, and the dt's cancel. This is not, of course, not mathematically precise, but it can be made so. So this is going to end up being the integral of this from actually, let's make it an integral from t naught to t. So we're going to take the integral from t naught to t of both sides. And what we're going to get is this here is going to be x of t I of t, since it's an exact derivative to begin with, minus the lower limit of integration, so x of t naught I of t naught is equal to the integral from t naught to t of I am going to change variables here because otherwise things will get confusing. I of tau, g of tau, d tau. And note, as an aside, that the I of t naught is equal to, let's see, where did I define I of t? That's the exponential of x of the integral from t naught to t naught of a1 of tau d tau. But the integral from t naught to t, oh sorry, let me move this up so you can see. But the integral from t naught to t naught, well, that's just 0, right? So this is equal to the e to the 0, which is equal to 1. So the next thing we can conclude is that x of t I of t minus x of t naught, let's move the x of t naught onto the other side, is equal to x of t naught plus the integral from t naught to t of I of tau g of tau d tau. We can divide out I of t on both sides, and so then that gives us x of t is equal to 1 over I of t times x naught plus this integral. And if we expand out I of t, this is just equal to e to the minus the integral from t naught to t of a1 of tau d tau times x naught plus the integral from t naught to t of e to the integral from t naught to tau of a1 of, let's use u as our next variable, g of tau d tau. And so if we know that a1 is a constant, which is a very common case, if a1 is a constant, and we set t naught equal to 0, so we start at time 0, just for simplicity's sake, well, then plugging these things in, you get that x of t is equal to e to the minus a1t times x naught plus the integral from 0 to t of e to the a1 tau g of tau d tau. And if further, we know that this is homogeneous, so if g is equal to 0, then we get that x of t is equal to x naught e to the minus a1t. And so this is a homogeneous solution. Which is a long-winded way of saying that if you have a first-order ODE that is homogeneous, your solutions are of this form, they're these exponentials. Which is something that you should remember from your differential equations class. I'm going to go ahead and give examples now because I figure if you remember all this stuff, then you're probably just going to skip these videos anyway. And if not, it makes sense for me to have these examples in here since this is basically all just review. So let's start with a simple example. Let's say that we have dx dt minus x over t is equal to t e to the 3t. And x of 1 is equal to 2. So this is one of the examples in your textbook. I forget which number. I probably should have written it down. But let's let our integrating factor be equal to e to the minus the integral from 1 over t dt equal to e to the minus natural log of t, which is, of course, just equal to 1 over t. Let's multiply both sides by this. So we're going to do this in the... So multiply both sides by this. We're doing this in the indefinite form. So we have 1 over t dx dt minus x over t squared is equal to e to the 3t. And this turns out to be an exact derivative. So this is dxt inverse over dt is equal to e to the 3t. If you take the integral of both sides, you end up with x is equal to some constant times, let me write this out a bit more. So we have x over t is equal to some constant plus e to the 3t over 3, because you're taking the integral. And so therefore, x is equal to ct plus t e to the 3t over 3. And this shows us some of the various various parts of a solution to an ODE. You have a general solution, you have this actually turns out to be your homogeneous solution, and this turns out to be the particular solution. Since this is an inhomogeneous equation. If you want to solve for the solve initial value problem by plugging in, plug in x of 1 is equal to 2, well, then when we do that, you end up getting that 2 is equal to c plus e cubed over 3, because t is equal to 1. And so therefore c is equal to 2 minus e cubed over 3, which gives a final solution of x of t is equal to 2 minus e cubed over 3 t plus t e to the 3t over 3. So solution to the initial value problem. Okay, so that's first order equations. There are several other ways of solving first order equations, which I'm not going to cover. You can also do a direct integration. That's probably one of the methods you're a bit more familiar with, since you would have had a lot of practice on that in B44. And there are a couple of other methods as well. But yeah, so just in general, recall that a general solution to an nth order, this is first order, but let's talk about nth order, linear, non-homogeneous ODE is the sum of the homogeneous solution and the particular solution. So we have x general is equal to x homogeneous plus x particular. And furthermore, the general homogeneous solution, xh of t, is the sum of, is a linear combination where ci are arbitrary real constants of phi I of t, where our phi I of t's are n linearly independent solutions. To the homogeneous equation. So where you set g of t equal to 0. And sometimes we call these fundamental set of solutions. And now we're going to specialize down to constant coefficients. Since it turns out there's a lot we can say about constant coefficients. Let me put this in blue. Constant coefficients. So above, our coefficients could be functions of t. Suppose they're not functions of t. Well, then you have a difference equation of the form the nth derivative of n, or sorry, the nth derivative of x plus a1, the n minus 1th derivative of x plus dot 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 a n minus 1 x dot plus a n x, where each of our ai's is, of course, a real constant. Well, then we can get the characteristic, let me actually write that down. We can get the characteristic polynomial. The characteristic polynomial p of lambda is equal to lambda to the n plus a1 lambda to the n minus 1 all the way through a n minus 1 lambda plus a n. The zeros, or roots, so the roots of p of lambda, sometimes also called eigenvalues for reasons that you should remember from Mat B44, and that will become obvious when we explain the correspondence between higher order linear ODEs and systems of first order ODEs. So something called the eigenvalues of the ODE give us a set of linearly independent solutions. What are these linearly independent solutions? I'm going to write them in the general form. So they're exponential functions, but they sometimes have t, some power of t in front of them. So it's t to the beta e to the lambda t, where beta is equal to 0, 1 through m of lambda minus 1, and m of lambda is the multiplicity of lambda as a root of p of lambda. And let's give a couple of examples. So if we have p of lambda is equal to lambda to the fourth minus 1, and so this is the characteristic polynomial of the equation d to the fourth derivative of x with respect to t minus x is equal to 0. So if you have this, well, we have our characteristic polynomial. We factor it and set it equal to 0. So this is lambda squared minus 1 times lambda squared plus 1 is equal to 0. So lambda is equal to plus or minus 1 and plus or minus I, the imaginary number. So we get that and each of these has multiplicity 1. And so t to the beta is always 0 because it goes from 0 to 0. Beta only ranges from 0 to 0. And so the solutions are e to the t, e to the minus t, e to the it, and e to the minus it are solutions. And then the general solution to this, since this is a homogeneous equation, and so we don't have to worry about solving for particular solutions. So the general solution here is just x of t is equal to c1 e to the t plus c2 e to the minus t plus c3 e to the it plus c4 e to the minus it. Okay, so that was an example where all the roots had multiplicity 1. What if the roots have higher multiplicity? So let's say p of lambda is equal to lambda squared minus 2 lambda plus 1. So this is the characteristic polynomial of the homogeneous equation x double dot minus 2x dot plus x is equal to 0. Well, we get lambda minus 1 squared is equal to 0. So lambda is equal to 1, and m of lambda is equal to 2. So the multiplicity of the only root is equal to 2. So e to the t and t e to the t, that should be a t, are solutions. They also happen to be linearly independent. We're not going to prove that here, but it was proven in differential equations. So in the x of t, the general solution to the homogeneous equation is going to be c1 e to the t plus c2 t e to the t. Now, it's actually a little bit important sometimes when you want real solutions to remember that the span of e to the a plus bi t and e to the a minus bi t, where a and b are real, is equal to the span of e to the at cosine of bt and e to the at sine of bt. And this is something you can figure out from Euler's equation. And so going back to the first example, so for x, the fourth derivative of x minus x is equal to 0, x of t is equal to, another way of writing it is equal to c1 e to the t plus c2 e to the minus t plus the c3 cosine of t plus c4 sine of t. Okay, so there are several different ways you can write it. And if I'm asking you for a real solution, you do need to convert it into sine and cosines. If I allow you to write a complex solution, then obviously you don't. Okay, and let's finish off by proving a theorem, since this is something we haven't done in a bit. And this will actually be a theorem that's related to stability. So this will be the first new content, semi-new content at least. So if all the roots of the characteristic polynomial p of lambda are negative, or have negative real parts, let's say, have negative real parts, and some of the roots can be complex, and so we need to talk about them having negative real parts, and if it's a real number, well then if the number itself is negative, that has a negative real part, then given any solution, x of t, of the corresponding homogeneous ODE, there exist constants m and b greater than 0 such that the magnitude of x of t is less than or equal to m e to the minus bt for t greater than 0. And one of the obvious consequences is, given that that's true, you know that the limit as t goes to infinity of x of t is equal to 0. That's proofless. Okay, so let's let lambda 1 through lambda r be the r distinct eigenvalues, and m of lambda be the multiplicity. Well, then we know that x of t is going to be equal to some linear combination of the double sum from I equal 1 to r, and j is equal to 0 to m of lambda I minus 1. Cij t to the j e to the lambda I t, where we have a bunch of constants. And we're going to let our value b be some value less than the minimum over I equal 1 through r of the absolute value of lambda I. Oh, actually, let me change this to the minimum of the absolute value of the real part of lambda I, which is actually a little bit important for our next derivation. So then what we want to do is note that the absolute value of t to the j e to the lambda I t e to the bt, and the bt here comes from over here, and we're moving it onto the left-hand side just because it's a little bit easier to reason about it there. So this is equal to t to the j e to the real part of lambda I plus b times t. Why is this the case? Well, it's because e to the it, or e to the ia for any imaginary number, it just goes around the unit circle, and so the modulus of that is going to be equal to 1, and so you can factor that out. And so you can factor out the imaginary component, and so you're left with the real component, and of course when you multiply together exponentials, you're adding together the exponents. And we know that the limit as t goes to infinity of t to the j e to the real part of lambda I plus b times t is equal to 0. Why is this? This is because the limit as t goes to infinity of e to the minus kt for a positive value k over t to the j, e to the j e to the minus kt is equal to 0 for all k greater than 0. So this is basically, this is basically just saying that exponentials, if something's going exponentially fast to 0, even if you're multiplying it by something that's growing polynomially fast, it's still going to go to 0, because exponential growth is, well, bigger than polynomial growth. And that's something you can check using standard calculus techniques. So we're going to take that for granted here. So this implies that so note that this entire thing goes to 0, right? So this implies, since it goes to 0 and you have some initial starting point, Well, this implies that the entire thing is bounded. So there exists some mi greater than 0 such that this entire thing, t to the j, e to the lambda I t, e to the bt, is less than mi, which is equivalent to saying that the absolute value of t to the j, e to the lambda I t is less than mi e to the minus bt. Okay, so we're starting to get close to where we wanted to show. So what we've done is we've shown that one of these solutions is going to be less than mi e to the minus bt. Well, at this point, it's pretty easy. We've just showed for each of our various fundamental set of solutions, and then we find some constant that's bigger than all of them. So let's let m naught be equal to the max over all of our coefficients. And then we let our m variable be equal to m naught times the sum over j1 to r, j1 to m of lambda I minus 1 of mi. So basically we're adding together all the mi's, and then we're multiplying them by some upper bound on the coefficients, ci's. And once we've done that, then we know that x of t is less than or equal to m times e to the minus bt, which proves our theorem. Okay, so now what does this have to do? What does this have to do with stability? Well, what we're basically saying is that if you have a linear ODE, if you take a look at the roots of the characteristic polynomial, you can tell whether or not something's stable by whether all the eigenvalues have a negative real part. If all the eigenvalues have a negative real part, then the 0 point is locally asymptotically stable. We'll be getting into this in some more detail, and this will turn out to be one of the key pieces of stability analyses of nonlinear ODEs as well, which we'll linearize by using things like the Jacobian, like we did for difference equations. Having said that, that ends our brief whirlwind review of linear differential equations. We'll talk a little bit more about, we'll review some more concepts about ODEs in the next couple lectures, but we'll start mixing in some more of the mathematical biology and dynamical systems stuff that we've been dealing with in the difference equation half of the class. So thank you very much, and I'll see you in class.